Think of the edge of the network, and you might picture a sleek, weightless digital frontier. The truth is much heavier. It is the heavy, heat-stressed reality of a 5G multi-access edge computing node. Telecom operators have poured billions of dollars into 5G radio access networks to provide massive bandwidth. Yet the actual compute capacity sitting at these local base stations often remains completely idle. There is a persistent assumption that edge computing simply means taking a standard cloud data center, shrinking it down, and dropping it at the base of a cell tower. But a base station operates under uncompromising physical limits. It has a tiny spatial footprint and absolutely no capacity for the massive, power-hungry cooling systems that hyperscale data centers rely on. You cannot outcode a thermal bottleneck in a metal box sitting in the summer heat. Hardware physics, not cloud software architecture, ultimately dictates whether artificial intelligence can survive at the edge. If you look at why edge inference struggles today, the common diagnosis is a lack of raw computational throughput, or FLOPS. The assumption is that we simply need faster processors. Cramming more processors into an edge node is a dead end. Every extra operation increases the power draw, which quickly hits the strict thermal ceiling of the hardware enclosure. The actual structural constraint is the memory wall. The bottleneck is the immense energy tax required to physically move data back and forth inside the hardware, from memory to the processor. To successfully scale AI at the edge, operators have to solve this memory wall through strict hardware-software co-design, integrating intelligence directly into the radio access network. When software adapts to these physical constraints, the edge node stops being a passive transit point. It becomes an active intelligence layer capable of processing data where it is produced. To see exactly where edge accelerators are failing, we can look at a 2021 characterization study conducted by Google on their own edge TPU. The scatter plot maps the performance of 24 different neural network models. The horizontal axis measures computational throughput, while the vertical axis represents theoretical energy efficiency. Notice how the actual data points cluster significantly below the peak theoretical limits of the hardware. That massive efficiency gap is not caused by the processor struggling with multiply-accumulate operations. The drain comes almost entirely from the memory system. Moving a single piece of data from the memory block to the compute unit consumes orders of magnitude more power than actually performing the math. Inside a 5G base station, every watt of that wasted power translates directly into physical heat. If telecom operators attempt to run standard cloud-heavy AI models on this local hardware, that memory tax forces the system to thermally throttle or fail entirely. Data movement is a literal heat generator. Without radically redesigned architectures, that energy tax will melt edge infrastructure before it ever reaches peak performance. Ending the data movement tax requires moving the compute logic to the memory itself, a hardware architecture known as processing in memory, or PIM. This schematic compares the two approaches. On the left, a traditional setup wastes energy pushing data across a long physical bus from the DRAM block to the CPU. On the right, the PIM architecture removes that pathway entirely, embedding the compute units directly inside the memory arrays. By collapsing the physical distance, the system performs its computations exactly where the data already lives. Research from ETH Zurich examined several variants of this approach, including UPIM, SIMDRAM, and MENSA. MENSA's 3D stacking technique proved especially effective for the strict spatial constraints of the edge. This architecture is critical for memory-bound inference workloads. Tasks like running transformers or convolutional neural networks at the edge are restricted by memory bandwidth, not processing speed. Processing in memory turns the memory block from a passive storage bin into an active computation engine. It attacks the thermal choke point at its source. Upgrading the silicon is only half the equation. Software must be optimized to match. At the edge, manually tuning hardware for specific algorithms by human engineers is an obsolete practice. The modern standard for edge deployment relies on Neural Architecture Search, or NAS, to automate the process. This is true hardware-software co-design. The system simultaneously optimizes the structure of the neural network, the architecture of the accelerator, and the compiler mapping. This bar chart shows the results of a joint search system called NAS, developed at Shanghai Jiaotong University. Compared to a human-designed accelerator known as Iris, the NAS system achieves an energy delay product that is 4.4 times lower, operating entirely under the exact same compute budget. Driving down the energy delay product by that magnitude without adding processing power proves that the software must adapt to the physical constraints of the hardware. For operators deploying edge networks, the testing protocol has to change. The focus must shift away from raw compute benchmarks and towards measuring the energy delay product under simulated thermal duress using NAS regression networks. Software has to be strictly hardware aware. Algorithms that ignore the physical limits of their enclosures will simply fail at the edge. These architectural theories are already operating in mission-critical deployments today. Look at the ESA FISAT-1 satellite orbiting Earth, or ZF Friedrichshafen automotive ECU boards carrying ASIL safety certifications. Edge inference is already product-grade in aerospace environments, where cloud connectivity is structurally impossible, and in the automotive sector, where autonomous driving requires zero-latency safety. While inference handles the execution of pre-trained models, on-device training allows networks to update and learn from local data without a cloud connection. This schematic illustrates the resource-constrained training model developed by A-Star. It relies exclusively on quantized neural network weights packed tightly inside an outlined on-chip memory boundary, blocking any data requests from an off-chip zone. By confining the entire training process within the limits of the on-chip memory, the system completely eliminates the energy tax of moving data off-chip. Operating autonomously also requires strict local security. Systems need integrated inference latency prediction to safely route workloads among edge devices, ensuring raw data payloads are never exposed to vulnerable external networks. True edge intelligence means severing the umbilical cord to the cloud. It is the ability to learn, adapt, and secure data entirely locally. Zooming out from the hardware, these physical constraints dictate the macro infrastructure war. This topology map illustrates massive data streams bypassing local base stations entirely, flowing directly into a centralized hyperscaler cloud. This dumb pipe model actively benefits hyperscalers by forcing high-margin inference workloads into their data centers. It creates severe economic imbalance. Telcos carry the massive 5G capital cost, while hyperscalers extract the lucrative margin. Beyond the finances, there are strict operational consequences. Sending localized data halfway across the country introduces unacceptable latency risks and massive backhaul costs. Treating a multi-billion-dollar 5G infrastructure purely as a transit mechanism is an economic drain on operators and a structural failure for mission-critical AI. The Telecom counteroffensive is RAN integrated orchestration. The data stream to the hyperscaler cloud shrinks, and intelligence routes to compute nodes directly at the 5G base stations. Pending patents from companies like SK Telecom show this shift is underway, pushing AI orchestration directly into the radio access network. By deploying multi-agent orchestration locally, telcos can transform their idle, physical base stations into highly lucrative execution hubs. But executing this power shift relies entirely on overcoming physical limits. It requires solving the memory wall through processing in memory architectures and hardware-aware software design. Distance is a tax, and physics wins. By solving the memory wall, operators move the control point from distant data centers to the local tower, reclaiming the high-margin compute that hyperscalers currently own. At the edge, physical thermal limits are the